Welcome to this explainer. Today, we're taking a really fascinating journey into the heart of machine learning. Our big goal here is to take the sometimes abstract, dense math of model tuning and translate it into clear geometric intuition that you can actually visualize. We are going to completely demystify regularization, specifically focusing on the absolute powerhouse techniques of L1, L2, and elastic net. Let's get started. Okay, let's dive into this. Pretty much every data scientist at some point has faced the central conflict of machine learning. You know the drill. You build this highly flexible model, you feed it data, and it looks like a total genius. But then you test it on new, unseen data, and it just completely fails. Why does it do that? Well, because the model didn't just learn the underlying signal, it actually memorized all the random noise. So the fundamental question we're answering today is, how do we mathematically enforce discipline to stop algorithms from doing exactly that? To really understand this, we've got to look at what's called the complexity wedge. When a model is highly complex, it heavily inflates your in-sample predictability. I mean, it looks absolutely perfect during training, right? But this creates a massive shortfall in out-of-sample performance. The model just simply doesn't have enough data relative to its huge number of parameters to figure out the true mathematical reality. This shortfall right here represents the limits to learning that are caused by unconstrained complexity. So here's our roadmap for today. We're going to hit the overfitting problem, define what regularization actually is, and then open up our statistical toolbox to look at L2 ridge regression, L1 lasso, and finally, how we combine them using the elastic net.
Starting off with Section 1, the overfitting problem. Now, before we can appreciate the cure, we really need to understand the disease. Let's contrast these two extremes. On one side, we have high bias. We're underfitting. This is the model that's just way too rigid. It completely misses the underlying trends in the data. But on the other side, we have high variance, overfitting. A high variance model is just wildly chasing every single data point on the graph. It literally contorts itself to capture all the random errors, outliers, and statistical noise as if they were actual true patterns.
Let's ground this in a real-world scenario. Consider the 1,000 predictor problem from the finance world. Imagine you're trying to predict monthly stock returns using a massive panel of 1,000 different variables. Financial data has an extremely low signal-to-noise ratio. If you just throw a standard, unpenalized linear regression model at a dataset like this, it completely collapses. Because the number of predictors is getting so close to the number of observations, the model becomes wildly inefficient. It just overfits all that financial noise instead of extracting the tiny hidden signals we actually care about.
Which brings us to Section 2. What exactly is regularization? This is the conceptual hero of our story, the mathematical mechanism that directly fixes that high variance problem we just talked about. By definition, regularization means adding a penalty term to our standard error function. Normally, an algorithm's only goal is to minimize error, but with regularization, we give it a strict budget. We're basically telling the model, you want to minimize error? Great, but you now have to pay a mathematical fine for every complex weight you add. It forces the algorithm to compromise between accurate empirical predictions and the overall size or complexity of its solution. Let's move on to Section 3, the L2 penalty, also known as ridge regression.
All right, let's open up our regularization toolbox and look at our first tool. The L2 penalty works by taking the sum of the squared parameter values and adding that directly to the loss function. Because it squares the values, it severely punishes extremely large coefficients, shrinking them down nice and smoothly. This makes the model highly robust to collinearity, those situations where features are highly correlated. But crucially, because the penalty gets smaller and smaller as the weight approaches zero, L2 almost never drops a feature entirely. It just kind of shrinks it. Now, what's really interesting about this next slide is Section 4, the L1 penalty, or the lasso. So L1 introduces a completely brilliant fix for L2's inability to drop useless features. It replaces the squared values of L2 with the absolute values of the parameters. Now that might sound like a minor mathematical tweak, but trust me, it changes everything. Instead of just shrinking weights smoothly, L1 ruthlessly drives some of those coefficients to exactly zero. This creates what we call a sparse model, effectively acting as an automated feature selector that completely turns off the inputs that just don't matter. And this brilliantly illustrates why that happens geometrically. Look at the green shape there. That is the L1 constraint region, shaped like a sharp diamond. The concentric ovals represent our error function's level sets. As the error tries to minimize itself while staying within our L1 budget, the expanding oval is geometrically forced to hit the sharp pointing corners of the diamond first.
And because those corners sit exactly on the axes, well, actually, it mathematically forces one of our parameter weights to precisely 0. These are known as attractive corners, and they're a total game changer. Building on that geometry, notice that completely flat horizontal line right in the middle around 0. That right there is the strict sparsity of the L1 penalty doing its job. Unlike L2, which would just show a sloped line getting closer and closer to 0, L1 creates this dead zone where features are just abruptly dropped right out of the equation. So the absolutely crucial thing to take away here is this continuous contrast between the two. L1 uses absolute values and creates a sharp diamond shape, forcefully zeroing out features for selection. L2 uses squared values, creating a smooth circle mathematically, which just shrinks weights to handle collinearity without dropping them. Once you lock in this mechanical and geometric difference, you basically understand the core of how regularization works. Which brings us to Section 5, combining forces with the elastic net. So what if we want the best of both worlds, right? What if we need the sparsity to drop useless features, but we also really want the parameter shrinkage to handle correlated data? That is exactly where the elastic net comes in. It literally combines both the L1 and L2 penalty terms into a single loss function. You control the blend using a hyperparameter, allowing your model to leverage varying degrees of both the ridge and lasso effects. Returning to our brutal 1000 predictor stock market test from earlier, when researchers applied the elastic net, that unpenalized collapse we saw completely reversed. The model successfully navigated the noise, achieving a massive out-of-sample Sharpe ratio of 1.33. It survived because it could drop the absolute junk while simultaneously shrinking the correlated signals. I also want to just quickly highlight how these exact concepts bridge over into modern deep learning. Notice the dashed vertical line here representing early stopping, which is just halting the training before the network can fully memorize the noise. Geometrically and mathematically, early stopping acts just like an L2 weight decay regularizer. By stopping that journey toward the absolute minimum error, you artificially shrink the network's weights, giving you the exact same regularization benefit. Which leads us to a really fascinating final thought to wrap this all up. By adding these L1 and L2 penalties, we are intentionally stopping our models from finding the true mathematical truth of our training data. We are artificially biasing them, on purpose. But if an unbiased model wildly overfits to noise, we kind of have to ask, is a perfectly unbiased model ever actually useful in the complex, messy reality of the real world? Thank you so much for joining me on this explainer. I really hope this sparked your curiosity, and I highly encourage you to ponder the true statistical cost of an unbiased model. Keep learning, and I'll catch you in the next one.